We're starting chapter 6, which deals with rational expressions. And we're going to do some multiplying and dividing, some of the rules. Now you might recall that rational expressions refers to fractions. So in a sense, we're dealing with algebraic fractions, where you might have variables in the denominator as well as the numerator. And for example 5 and 6, they're showing us some function notation of rational expressions. And they want us to find these values of x. And what we said when you do something like this, and again, part of it is strategy, make a t-chart, where remember this could be the y, and they're giving you the values for x as 0, 3, and -1. And then later, when they change the function notation to r of t, they're giving you values for t. Now, what I've done is I've put the answers in, as the answers are in the back of the booklet. But again, you want a strategy to do that. Now, I'm not going to do them all, but we can do at least one to see what it's like. So for this first one, we're going to put a 0 where the x's are. So if we put a 0 there, this becomes a 0, and this is a 0, so we're left with, in the numerator, just a 5. And then our denominator, the x is a 0. So that one was easy. The answer is 5/4. Now let's put a 3 there. And this is the technique we want to stress. So you're going to put 2, then a parenthesis where the 3 would go. And we're going to square that. Then a -3, that's straightforward, plus 5. And that's going to be over 4 minus 3. So the key to doing any of these, and we've done them pretty much in every chapter where we're asked to substitute, is, again, use the parenthesis, and then carefully watch the signs, and then now order of operations. So the first thing they want us to do is to square the 3, which will be 9. So 3 times 3 is 9. 2 times 9 is 18. 18 minus 3 is 15. So far we have 15 plus 5. Our numerator is going to be 20. And then we go 4 minus 3 is 1. And when we write that answer, we don't usually put it over 1. Every number is over 1. So it just gives us a 20. So in here, we would be substituting next a -1. And again, working it through to get your answer. Now I thought one over on this side. Again, I'm not going to do them all, but where it does not exist is the answer. So let's substitute a 1 for our t's here and work on that one. So it'll be 1 cubed minus 5, and then 1 squared minus 2t plus 1. I got to put the t there though, is 1. Now I could probably put that in parentheses. There we go. So, 1 cubed is 1. 1 minus 5 is a negative 4. 2 squared is 1. So that's 1 minus 2 plus 1. So here we have 2 minus 2. So our denominator is going to become a 0. So anything divided by 0, we say does not exist, and we would have used undefined. And I guess they're using that as a synonym. And the other answers, again, this video is meant to show you how to work them, not necessarily to do them all. We want to deal with strategy here. As we continue with rational expressions, and again, fractions, they're going to ask us to do various things with them. For instance, here they're asking us to find the domain of 7 and 8. And when we think of domain, what we're thinking about is a value of x that would make this denominator a 0. So when we're asked in rational expressions to find the domain, all we're interested in is the denominator and what value of x would make that denominator a 0. Because then it would be undefined. Well, the way we do it is we just say negative 4x equals 0. We equate the denominator to 0 and then solve. And we're going to divide both sides by a negative 4. And we get x equals 0. So if x were 0, this denominator would be undefined. So we cannot include the possibility that x would equal 0. So one way of indicating it is says x cannot be 0 in the domain of that value of x. And they also ask us to write it in interval notation. And how would you write that? And the answer would be that you could have values of x from negative infinity up to 0, but not including 0. So we'd use a parenthesis. Then the union symbol, starting again at the other side of 0, going to positive infinity. And that would be the domain of this function. All right, jumping down to number 8. Again, we're not interested in the numerator, just the denominator. And I'll take a little shortcut and just say on the denominator equals 0. This is from a previous chapter. We factor this. And as we factor it, we see the difference of perfect squares that we will put into their conjugates. And therefore, our values of p in this denominator would be p would equal a negative 5, or p would equal a positive 5. But again, these are values that we are excluding. So how would we write that in interval notation? Well, again, it's from negative infinity up to negative 5, parenthesis, union, again, starting at negative 5, up to a positive 5, union, starting at 5 again, and then up to positive infinity. Almost ran out of room there. So again, other classes, the way we would show to write it, we just say that x cannot equal a negative 5 or a positive 5. To put it in interval notation, we'd have to use this method here. Now, going on to example 9, this is where we start our next section, and it's sort of simplify these rational expressions by canceling out any common factors that you might find in them. Okay, 48. And let's develop a strategy. 48, as I look at it, is 6 times 8, let's say. And this is 4 times 8. And I can actually see another 2 in there, so the 8s would cancel out. So this would be like, actually you could factor a 16 out of there, and that would go 3 times. 16 would go out of there twice. So that gives me my 3 and my 2. So again, you're going to have to develop a method to cancel out common factors. So I saw a 4 times 8 and a 6 times 8, and then I realized it's a 2 times 16, 3 times 16, so I'm canceling out a common 16. And then for exponents, you're just going to subtract as you cross the division bar. So here you're taking 2 A's out from there, and you're just left with a 1A. Here you're going to cancel out a 1, and you're going to be left with a 4. So it looks a little bit messy, but our final answer is going to be 3 halves. And then in our numerator, there's only going to be a 3, while in our denominator, we're going to have b to the 4th. And let me just check that. Oh, there was an A left up here too, so I have to, yeah, there's my 1 from the A. Okay. Hopefully as you do it, you're going to have a little more room. As we go on to number 10, and again, strategy. What kind of jumps out at you from number 10? Well, I can see a 6 here and a 6 here. So I'm going to factor out from the top a 6. And I see a 6 on the bottom as well. And you might say, wow, just in one example now in chapter 6, we're doing 2 examples from chapter 5. Yes, that is true. It's a lot more intensive. So you might say, what are common factors here now? Well, the 6. So your final answer for number 10 is x plus 5 over x minus 2. Now, you might say, can you cancel out the x's now? And the answer is no, because x's, as you write it again, these are not factors. The x's are not factors. They're terms. And as we say, you can only cancel out common factors. 11 is similar, so is 13. But we'll do 12. Again, we're showing you strategy here. And we're asked to simplify. Well, it's nice if you can recognize that this is the difference of perfect squares that will factor into its conjugates. Now remember, you could make this one negative, this one positive. This is my preference. And as you look at that, you can see you could factor out a common x. Did I copy that correctly? Number 12? No. Should check my work more carefully here. All right, so that's x squared there we go. So, again, this part's correct. I had the wrong one here. And I don't know if you recognize this bottom one. This is the perfect square trinomial difference of perfect squares, something we had done in chapter 5. So, we factor it into its conjugates. Now this I know is going to factor into a binomial square. And now we look to see, are there common factors? So our final answer is x minus 6 over x plus 6. Can we cancel these out? No. These are now terms. And I apologize for not having that correct, but we did catch it in time. 13 is very similar. I will do number 14 and number 16. Again, we're picking up examples to show you strategies. Now you might say, could I cancel out my t-squares here? And the answer is absolutely not. Why not? Because these are not factors, these are terms. You can only cancel out common factors. So what do you do here? Well, you factor this. And fortunately, they're not too hard to factor. Using our rules from chapter 5. Now you might say, well, I didn't finish. Yes, I want you to do something too. You want to put the signs in here. So here, this is a negative 7. This is a positive. So both of these have to be negative. And if you FOIL it, you get to check it, and it does check. Now for this bottom one, this middle term is a negative 1. So this is going to be negative, and this will be positive. Because my last term here is a negative 20. And often, you know, again, they're having you do this because somewhere something's going to cancel out. So your final answer is t minus 2 over t plus 4. Now they are also asking us here to define the domain. Well, again, we're only interested in the denominator. So for this one, to make this part a 0, even before you cancel out, x, or let's say in this case t, cannot be a -4, or t cannot be a +5. You'll see those answers in the answer key, and that's where they get them from. Now you might say, shouldn't it just be the -4? And the answer is no, because this was your original expression in the denominator. So you have to include the original factorization as to what would make the denominator a 0. Now, as you look at example 16, again, they're not just a trinomial divided by a trinomial. Here, it's multiplication, but they don't want you just to FOIL or multiply. Really, what they want you to do is factor, simplify, and then leave your answer in factored form. So let's start factoring. Here we can take out an x, and we're left with x minus 2. All right, that can't be factored anymore. Here, again, they're not too difficult. Because you're looking for factors of 6 that add up to 5. So now I factored this completely. And here we have a perfect square trinomial that will factor into the binomial squared. And this will all depend how quickly you can do it as to how much you remember of that from chapter 5. And this one, I'm going to factor out an x squared first here. And then I get x to the x second minus 4x. Minus 4, no x. I'm factoring out the x squared. So I get x squared minus 4. That's better. Now, when I factor that, I get an x squared. And then this is the difference of perfect squares that I will factor into its conjugates. And now I have completely factored this multiplication problem. And now what I'm going to do is cancel out wherever I can. And I can cross cancel out because this is multiplication. So I have an x plus 3 there, x plus 3 there, x minus 2 there, x minus 2 there. Now I have an x to the first, x to the second, so this gets canceled out and this just becomes x. So my final answer then is on top, I'm going to have x plus 3 all over x plus 2, the quantity squared, and I have an x there that I'll put right up here in front. And I believe that's good for number 16, and that is correct. Now, remember, they give me the answers, but what I'm showing you here is that I could actually, I've actually worked these out, okay? Okay, let's do this next one here. Now, we're changing a little bit what we're doing, here we were multiplying. Now we're going to divide. And you might say, how do you know it's going to be divide? Well, because of the division sign. Now, in division of fractions, there's a general rule that we follow. And that basic rule is we change all division of fractions to multiplication of fractions. And that's done by taking the second term and using its reciprocal, or just flip it over. So the 45D now goes into the denominator, and the 49 49 c to the 7th goes into the denominator. So we just flipped it. The first term stays the same. And now you can cross cancel wherever you can. Well, this is 28 is a 4 times 7, and 49 is 7 times 7. This is 3 times 9, and this is 5 times 9. I'm just showing you factors of these numbers. And then what we do is we can cancel out here the 7. Here we cancel out the 9. So as far as our number goes, we're now going to get a 20 over 21. And now we just have to deal with the letters. So here, this is d to the 1st. We're going to subtract it from the 8, and this becomes d to the 7th. And our c to the 5th, we're going to subtract, and we're going to get c to the 2nd. Now, we probably could have put that alphabetically. That's the way they usually do it, but that's okay as well. So for number 19, yes, that looks good. Okay, as we continue, I'm not doing them all, but we want to show you the strategy for doing them. Now, also to save writing, this started out as a division. I took these, flipped it, so now I have it as multiplication. I'm doing that for both. Originally, they'll have this as a division problem where this was flipped. So the strategy is the same for multiplication. You're going to factor this. Here we're going to factor out a 3. Remember, these are all techniques from Chapter 5 that you're working on. And then this is the difference of perfect squares. And generally, they're not difficult ones. We need a negative, so this will be negative and this will be positive. So as we cancel out, this will cancel with this. This cancels with this. And what we're left with then is x plus 2 x plus 3 all over 3 times x minus 5. So even though they want us to divide or multiply, they really want us just to factor and simplify and put our answers in factored form. And let me just check that. 21. Yes, that is correct. All right, let's go on to 24. Now, 24, they've gone from simple rational expressions now to functional expressions where they want us to divide. And I've changed from division to multiplication by flipping these two expressions. It just saves me writing it again. Now, as you're doing your homework log, you can do that too. You don't have to write the original problem. You can flip it. That'll save you a little bit here. So, factor, difference of perfect squares, and by foiling, you can check to see if you're right. And by the way, as I mentioned before, I did all these. I'm writing it out for you now, but I personally sat down and did the work for these. And actually, I found one little error somewhere that I will tell you if I spot it again. So what do you do now? Well, what are common factors? And I see this one, and this one. And that's about it. So x plus 3, x plus 5, over x minus 1, x minus 4. Now, if they wanted us to figure out what would be the domain of this original problem, I believe they are asking for that there. You might say, well, what do you have? Well, you'd say here, x cannot be a positive 1, x cannot be a negative 4, x could not be a 3, and x cannot be a positive 4. We had a negative 4, here's a positive 4. But there's one other thing, that in that original problem, when this was down there, we had the 5 that was there too. So you have to think of, because we got the 4 already over here, that would be a negative 4, but x cannot be this negative 5 up here, because in its original position, this term, this expression was down in the denominator. So that's why there are 5 things there. That was kind of interesting. Okay. As we go into the last 2 examples, again, I'm not sure how far each instructor will be going into the course, but I thought this word was sort of interesting here. Asymptote. I even looked it up on the internet under the wiki there or whatever, and what it refers to is in some graphs when you have a line that is approaching, as this curve that you are plotting approaches, in this case, the vertical axis, this vertical axis is the asymptote. It's going to be where it approaches 0 but never quite reaches it in these values. So the horizontal asymptote would be in this case, the x-axis, and in this case, it's the y-axis. So again, I don't know how much you're going into that, but I thought it was interesting to take a look at it. Here we see the function of g is this, so we factor it, and I've done that. And then we see that these cancel out. Now keep in mind that when you graph this is a parabola, but notice that when we actually work it, it cancels out, and all that is left in the denominator is x minus 3. And then if we were to find the domain, we'd see here that it's all values except x cannot equal 3 for this value. And again, it gets a little complex, but the vertical asymptote then for this expression happens to be 3, which we could dot in like so. So the vertical asymptote for this particular expression, once we did the factoring and canceled out our x plus 2's, the only one we're left with is x minus 3, but then that is equal to 0. So we say that the value that would be excluded from here would be a positive 3, and that happens to be our vertical asymptote. Okay, well, good luck with this. You're going to do some practice, some quiz bees, and eventually at the end you'll be taking a test. We'll be going on to topic 6.2.